This is the intro video for AP Calculus BC. We're going to be looking at Chapter 6 and specifically Section 6.1. So Section 6.1 is about slope fields, which is something that most of you have seen before, and something new, which is Euler's method. We're going to start off with some slope fields here. So a slope field is a graphical representation of a differential equation. So we've looked at differential equations a bit. And of course, let's remember that a differential equation is an equation that has one or more derivative or differential. On a graph, the derivative is the slope of a function, or perhaps a non-function, I guess, but slope of a graph, let's just put that. And so a slope field, all it really is doing is graphically representing slope at each point. So we're going to use little tick marks to help represent these, which are just little tiny line segments. And so a slope field could also be said to be showing local linearity, local being close by a particular point, linearity being a line. Let's keep in mind, I think we talked about this in the past, about how any graph, no matter how curvy it might be, if you just zoom in close enough, you look closer and closer and closer, every graph, curvy or otherwise, ends up looking like a line, and that's what these little slope fields are meant to kind of represent. So we're going to make a slope field here, as well as a solution curve. So let's take a look at example number 1. So in example number 1, we are given a differential equation right here, dy dx is equal to x minus 1, and we're asked to draw a slope field for that. And then once we're done with that, we'll draw the solution curve as well. So starting off, one of the best ways to do this is to make a little table. Your input will be x. The reason why the input is x is because the slope field only depends on x. Or I should say the slope only depends on x. And then your output will not be y, it'll be dy dx. We'll notice a little pattern with this one. Keep in mind that dy dx only depends on x, and that pattern will be kind of coming out as a result of that. So I'm going to just plug in a 0 for x, kind of our standard start spot there. So when x is 0, for an input, dy dx is negative 1. So what I'm going to do is come over here to my graph, and whenever x is 0, of course that would be the y-axis right there, I'm going to attempt to draw a slope of negative 1. So that'll be a challenge. There we go. So there's a slope field mark. There's another one. Oop, that one's a little curvy. Get rid of that one and try it again. Something like that. So those are all intended to have a slope of negative 1. Okay, when x is 1, dy dx would be 0. So that means when x is 1, which is this whole column right here, dy dx will be 0. So I'm going to attempt to draw in a 0 slope. Okay, that went in pretty well. And then when x is 2, 2 minus 1 of course is 1, so the slopes on this particular column would all be 1. So once again I'll try to sketch those in. That one's not very good. Let's try that one more time. There we go. Okay, and if we go over to the left a little ways, maybe we do negative 1. dy dx would be negative 2. So that means all along this column, dy dx will be negative 2. So negative slope, but steeper. Those are a little curvier than I would like. They should be lines. Let me try that again. Not bad. And then finally, when x is negative 2, dy dx, of course, would be negative 3. So these would be the steepest ones yet. Something like that. Okay, so there's a slope field. And the slope field tells us a lot of things. One of the things it tells us is the kind of the very rough shape of the solution curve. And so we are going to attempt now to draw that solution curve through the point 0, negative 1. So 0, negative 1, of course, is right here. So we're going to attempt to draw through that. Now what we want to be careful of here is we want to make sure that our solution curve goes through that point and mimics all the slopes around it, but we want to try to make sure it doesn't go through any other points. Sometimes that's realistically just not possible, but that's going to be what we want to shoot to do. So I'm going to attempt to sketch this in here. Let's try that again. Let's come from this side. And technically it probably should go through this point as well. So I'll leave that. But that would be our solution curve right there. Notice how it mimics all the slopes. As it passes through a particular column, it is matching those slopes. A couple of other thoughts about a solution curve. Number one, it has to be a function on the interval containing the initial condition. So in other words, containing in this case the 0, -1. Not only does the solution curve have to be a function, we also have to consider the domain. So we'll get into that maybe a little bit more when we do a few of these other solution curves later on in class. Okay, so slope fields. Hope that works for you. We're going to be looking at another video of Euler's method, which is also in 6.1 here coming up. It'll be a different video, so check that one out as well.